Okay,
Well, hello, everyone.
whenever you're ready, go ahead.
Okay, thanks, Ray. Hello, everyone. My name's Travis Humble. I'm at Oak Ridge National Laboratory. Among the many different things I do here, I manage our quantum computing user program. And so I want to give you some background on that today. Unlike the last talk, which gave, I thought, an excellent overview of some programming steps, this is actually going to be more background on what quantum computing is and how we have established a program at the Oak Ridge Leadership Computing Facility for getting access to some commercial quantum computing systems and testing out new ideas on those. Now, being at Oak Ridge, of course, I have a little bit of bias towards the OLCF systems. You can see the sequence here from Titan to Summit and now Frontier, which has been delivered and then currently being deployed. And what's unique about all these systems is they're massively parallel accelerator-based systems. And the acceleration here is going to come into play when we start talking about quantum computing as a potential quantum accelerator or a QPU. The motivation for this comes from the types of applications that we see are being run on these types of systems today. This pie chart shows a division by allocation of time. I think this is actually the 2020 Insight numbers that were used to make this pie chart, and roughly groups together codes according to the application areas in which they're used in. So physics and astrophysics, material science, chemistry. I think you'll immediately recognize that many of the applications running on these big computers are actually based in quantum mechanics itself. And that's an important point because quantum mechanical models are generally very difficult to represent, in part because of the memory requirements, but also because the fact that that memory, when it is distributed, generates not lots of non-local correlations that requires lots of communication in order to manage it. Now, it was nearly 41 years ago, Richard Feynman, Nobel Prize winning physicist, pointed out that if you want to make a simulation of nature, you'd better make it quantum mechanical. And this was just driving home the point that we were talking about, that the models that we're trying to simulate are intrinsically quantum mechanical, and the simulations of those models themselves can be quantum mechanical in the sense that we can use quantum mechanics for computation. And this gives rise to the field of quantum computing. And I'll talk more about what that means in just a second. But Feynman goes on to say, by golly, it's a wonderful problem because it doesn't look so easy. And this is the other side of the coin, is that in order to perform computation using quantum mechanics, you have to be able to control materials at the quantum mechanical level. So if you start building a computer, an atomic computer, in which you're controlling individual electrons, that's a very difficult problem. And the last 40 years has seen progress towards realizing this original vision of Feynman of using quantum mechanics for computation. So this is the only equation in the slide deck. It's just to summarize the point of what is quantum computing. Formally, it is quantum mechanical computation. It is using the wave function. That's the state vector psi of t that you see down here for describing information. Now, quantum mechanically, the state vector describes all information about my quantum mechanical system. If I can control that, in this case, by manipulating the Schrodinger equation, then I am able to perform computation itself. The reason this is not quite as easy it may seem on first pass is that quantum mechanics and this wave function are not intuitive concepts. To give you an example over on the right, if I think of the hydrogen atom, I mean, honestly, I normally think of a little proton sun being orbited by a little electron planet, but that's absolutely not what's happening in nature. In nature, you get something like the experimental image you see down here below, which is the actual electron distribution of a hydrogen atom. And you'll notice that while you can see things that look like orbit, they're actually smeared out over space, and that this is the wave function that we are imaging. So doing quantum computing is a concept in which we're manipulating that wave function via the Schrodinger equation that you see here. That comes through manipulating the electronic controls, the other thermodynamic controls that drive this generator, the Hamiltonian, in the Schrodinger equation itself. Now, if we are able to master control of the Schrodinger equation, it has been shown that there is actually a number of applications for scientific computing where quantum computers would be have an advantage. Up at the top here, you're seeing examples of these algorithms, quantum simulation, so that's solving Schrodinger's equation itself. Partition functions, which depends on summing over many different states of the system, discrete optimization, looking through noisy landscapes, machine learning for inference, factoring, which is actually a well-known example of quantum computing application, as well as several others. And what is interesting about these particular algorithms is that they can map into many of the same scientific domains that we were talking about in the earlier slide that drive allocations on our supercomputing systems. So high energy physics, material science, chemistry, biology, all of these are well-worn areas in which massively parallel accelerated systems have been applied for modeling and simulation. There's other areas too, though, of course, artificial intelligence, data analytics, operations and logistics. All of these map back to the quantum algorithms that have been shown, at least asymptotically, to have an advantage over their conventional counterparts. So the question is, can we actually demonstrate that advantage in a real application? In order to do that, we're going to have to build quantum devices for quantum computers. And today, we're at a point where we have prototype quantum processing units built on varying different technologies. You can see 4 examples here. I won't go through all of the physics of how these devices work, but I will point out that in all of these, what is happening is that the individual electrons, either in the atoms or the semiconductors or the superconductors or topological materials, are being controlled coherently. So they are being manipulated at the electron by electron level. You can see the types of devices that are doing that, the companies and universities that are pursuing this research. Most of the time, these are very small devices. You can see some sense of the length scale down here, 500 nanometers. They are oftentimes isolated from their environment. So this brings in thermodynamic controls in order to prevent noise and the loss of coherence in these manipulated electrons. But let me walk you through just an example of one of the leading technologies right now. It's a superconducting circuit-based technology. They're actually called transmons. You can see a picture of them over here. This is an example from IBM, well known, of course, in conventional computing, but the IBM quantum processors are actually some of the largest ones available today. This particular device has 16 qubits. Those are the fundamental units of information. Some devices scale up to 127. They are always in isolation from their surrounding environment. So that means electromagnetic shielding, ultra high vacuum, and cryogenically cooling. In fact, down to about 13 millikelvin, which is far colder than the dark side of the moon. The way that you program these systems is you actually send in a series of electronic signals. These waveforms then drive the dynamics in the transmons that represent the qubits that can be used to process information in the individual electrons. Now, currently, the fidelity with which we're able to manipulate these systems is limited by the errors that arise from noise in the devices. If you get, for example, a unexpected electron, that actually generates a source of charge noise that can then lead to errors in the operations that you're trying to apply. But present day systems like the one you see here, this is a dilution refrigerator in which that transmon chip is housed, can get down to 1% errors in the operations, the gates, and about 5% in the measurements. What's interesting about these types of systems is many of them can be accessed remotely. So the IBM systems, for example, have a cloud-based access model based on HTTPS. There's authentication and management and job queuing so that a user can write a program, we'll talk more about that in a second, that performs these gate operations, sends it over to the queuing system, at which it executes at some point and then sends back results, measurements from that quantum device. Now, the big question then is, well, are these devices big enough to actually tackle some of those scientific applications that we were talking about earlier? At present, we are finding that many of these devices can be used for demonstrating toy applications. What I mean now there is that normally we pare down the problem so that it fits into the available number of qubits. Over the past 2 decades, we've seen a growth in the number of qubits. This particular forecast for growth in qubits comes from a consulting firm, Yole Development, from last year. And if you can see it in your screen, this gray front was separating where 2021 was relative to the future. And what I can tell you is that we've already made progress to the right. The 127 qubit system is already up and functioning. The 433 qubit system is actually expected later this year. There's several other points on this diagram that have now emerged over just the last 9 months alone. So it's a very rapidly growing field, but we are still in the era of anywhere from 100 to 1,000 qubits, which is a very small number of bits of information and therefore still in the regime of toy problems. But those toy problems are an important part of how we evaluate whether or not we are properly programming these systems and whether they can eventually scale up to demonstrate some type of quantum advantage. So that's an overview of the state of the art for today and the types of technologies that are under development. What is going on at Oak Ridge is that we've established something called the Quantum Computing User Program that we run through the Leadership Computing Facility. And we procure access to these commercial quantum computing systems in order to perform testing and evaluation. There's 3 things that we're trying to do here. The first is we want to enable research. There's a lot of people developing quantum algorithms, quantum software, trying to generate applications that can demonstrate an advantage in these devices. And so we're trying to enable that spectrum of users to get access to these systems. At the same time, we want to evaluate the technology to understand where it is making progress. Does number of qubits really serve as the best metric for the performance of a system? Or is it error rates, or perhaps a combination of the two? And then finally, we want to engage the broader community, both the quantum computing community, which is very young and growing quickly, as well as the high performance computing community that includes the developers, the vendors, and ultimately the providers of these types of quantum accelerated HPC systems. So to do this, we actually procure access to multiple devices. We set up a user program. I'll talk about how you get access to that. Down here is the link to making a project application through the OLCF. The 3 types of systems that we have at the moment consist of the IBM system I was talking about earlier. That's a superconducting technology. Second type of system from Rigetti, startup in the quantum computing space, also based on superconducting technology. And then Quantinuum, which has developed an ion trap technology. And these 3 make up the resources that we have available in the program currently. Now, the program itself started almost 5 years ago. We've gone through a number of different technologies. D-Wave was a great example in terms of getting access to a superconducting quantum annealing technology. We've brought in simulators from Atos, and of course, had a number of other parts of this program active and with other vendors. What has been key, though, is getting users engaged with these devices. And for that, we've held user forums, training events. We're building up our staffing at OLCF to help with user assistance, science engagement, and technical integration. It turns out that all of that is important in order to actually have a quantum computing ecosystem, a set of users who can engage with each other and learn from each other and push the field forward, very much like the user forum that we're currently attending and as a way of advancing the state of the art. Now, the 3 systems that I were talking about earlier, you can just see here a few more highlights. The IBM systems, the largest one there has 127 qubits. The Rigetti system goes up to 80 qubits. Let me just say, even though both of these systems are based on superconducting transmon technologies, they actually come with different features enabled in them. One key feature is how do you lay out the connectivity between qubits? That turns out to be very important for the overall cost of executing programs, as well as the methods that you use to encode data into these memory-like devices. It's not as simple as just writing directly into the device. You actually want to come up with efficient ways of storing that information. The Quantinuum device based on ion traps goes up to 12 qubits. Here, the qubits actually represent individual atoms. And instead of having to have them in fixed geometries, you can reorient them through shuffle operations. And that again gives you a different type of way to encode information into the quantum computer itself. Now, of course, having access to experimental devices will always lead to the question of, did that do what I thought it should do? And numerical simulation continues to play an important role in verification and validation of these devices. For that, we have the Atos quantum learning machine. This is a dedicated numerical simulator. It provides up to 24 qubit models for simulation. And then, of course, the high performance computing systems are an alternative to this. But even using HPC, with the currently available memory and using brute force techniques for simulation, 50 to 60 qubits is about the largest system that you can expect to simulate. And I want to emphasize this point because we are already at the stage where the IBM 127 qubit system or the Rigetti 80 qubit system has exceeded our ability to validate their behavior using conventional HPC methods. And so that is a remarkable milestone for the state of the field, because it means now we are operating devices which, honestly, we're going to have to come up with better ways of checking their behavior than just brute force simulation. I want to highlight a few of the types of programs, projects that we have within the program. You can see here 4 columns. I'm not going to go into the details of the quantum mechanical or quantum computing techniques that were used. If that's your background, these are great resources, really great examples of how these quantum computing systems can be used. What I want to emphasize is the types of applications, the types of toy problems that we're talking about on these systems. In the physical sciences, we see things like chemistry has a very strong community right now because many quantum chemists already have a natural understanding of the types of encodings necessary to program a quantum computer. So this translation of the quantum mechanical state of a molecule into the quantum mechanical state of a computer has a slightly lower adoption barrier than some other areas. Now, that still doesn't mean that we've overcome all the hurdles. There is a number of different languages and programming models that can be used to actually perform this type of encoding step. And then, of course, the decoding step. How do I actually extract information out from the device after it's executed? I mentioned earlier, there's errors that arise both in the operation and in the measurement, and removing those errors, or at least trying to mitigate against them, is an important part of this type of work as well. So these physical science applications, and chemistry is just one example, tend to be looking at the raw representation of these quantum mechanical models within the quantum computing device. By contrast, there are other applications in the areas of data sciences and the applied sciences in which there is a mapping of a conventional problem, say, for example, graph theory, into a quantum mechanical model. And this is a really interesting point about how we actually have to twist the way that we think about conventional problems, cast them into a quantum mechanical setting, run them on the quantum computer, and then reverse that transformation. And by doing that, we may be able to tap into the features of quantum mechanics during the computation itself that gives rise to an advantage. And in several examples, there have been results in which searching through optimization for different landscapes finds that the ability to tunnel through barriers or sample the landscape in a entangled or parallel-like fashion actually lead to a detectable speed up in the time needed to solve those problems. And so these last 2 examples are actually emphasizing the ability to transform conventional models into quantum mechanical models and still accomplish some speed ups there. In terms of the user program's demographics, we actually have a number of different project types. So these are application areas, and I didn't include the key on here, but you can probably figure out astrophysics, computational fluid dynamics, chemistry, and so forth. I will point out that computer science and physics are the areas where we have the largest number of projects at the moment. I think this is driven in part by funding. We see a lot of support from the Oscar Program Office at Department of Energy, as well as the Basic Energy Sciences, but also by the willingness to adopt this new model of computation. Computer science in particular is looking to understand how we can actually program these systems, build the tool chains and workflows that they need in order to enable these other application areas. In physics, we're finding that it's the relative ease of translating the quantum mechanical model into the quantum computer that's driving a lot of activity there. But I wouldn't discount all of these other areas in which we're looking at these transformations of the conventional problems into the quantum mechanical mindset. Currently, the program supports over 200 users across all the available systems. These users are largely coming from the US. The national labs are well serviced. There's a little bit of bias on my part at Oak Ridge, but we also include universities, government, and industry users as well. Most project teams do have significant quantum computing experience. So the quantum computing user program is not where you come to learn how to program quantum computers. It's where you come after you've learned how to program quantum computers and you want to get some sense of testing the performance of these devices. Most of the time, the team consists of someone with quantum computing expertise supported by an application area of interest. Maybe it's tool chains and workflows, maybe it's astrophysics. It varies with project. There's a number of different programming languages and software environments available for these devices. Python is a very popular system, especially for rapid prototyping, but there are other languages, including C, C++ based approaches as well. We support over 50 active projects. We saw those on the last slide. Here, the funding is largely coming from Department of Energy, including the National Quantum Information Act, as well as several other agencies. I've talked about how we're focused on toy models. The other part is looking at device characterization, verification, and validation. You know, like most user programs through the DOE, what we are looking for are the results of this research. So we keep a close eye on publication count. Since we started counting this back in 2020, we've seen fairly rapid growth. We're now publishing at least one paper per week, and it looks like that's actually on the rise. So what are the steps to get access? This is actually going to be my last slide in the presentation. If you want to get access, go down to the link that you see here at the bottom over at OLCF. You'll have to submit a proposal that describes the merit of your idea. Again, if you're looking to just get first-time experience with quantum computing, there's actually other resources available. Feel free to reach out if you need some guidance on that. We'll collect that information and put that through our Resource Utilization Council, or RUC, in order to review the proposal, both for feasibility as well as its technical merit. Once we do some additional reviews, we'll notify the PI that it's been awarded, and then you can receive your project ID and start recruiting your users to the project. Of course, everybody gets vetted before they get on these systems, but we do have a user access, assistance, and science engagement teams on hand to help out when it comes time to start working with the devices. So with that, I will pause my presentation. I'll be happy to take any questions. Unfortunately, I don't have Slack installed on this computer, so this will require people to actually speak up. If there's any questions, I'd be happy to take them. Thank you.
Yes, how do you beat the coherence in quantum computing?
Yeah, so the question is how is the decoherence, right? So,
yes.
So like we were talking about earlier, in these devices where we're controlling individual electrons, when we write information into those electrons, it's stored as a superposition of states. Decoherence is the process by which that information would decay. Now, presently, in all technologies available, decoherence is one of the dominant limitations on how deep the programs can become. So how many instructions we can actually process. Every instruction takes a finite amount of time, and it kind of gets weighed against the decoherence, the decay of the information itself. At present, we find that relatively short depth of programs are essential for seeing good performance. The reason here is because of the decoherence. But the field is at the point where strategies for basically amplifying coherence, these are called error correction, so recovering from the decay itself, are starting to be tested. We have not seen on these systems an example where that actually works. I'll go back real quick to this highlight here in the middle on error detection improves accuracy. So here, error detection is actually being used to remove some of the errors that are coming from decoherence as well as errors in the gate operations. And this is a first example of how such strategies could be applied. But they haven't actually extended the coherence time yet. And I think that's one of the next things on the list for our application folks to test.
Hi, Travis.
Oh, hey there.
Hello. Maybe I'll make a general comment. Argonne National Lab actively is using this user facility, and we have a number of projects. So yeah, for example, on the screen is data science project, right? It's actually work done here at Argonne National Lab, and we do have agreement signed. So anyone at Argonne, if you're actually, especially at Argonne, if you're interested, just contact me and I'll help you to get access to this machine, and we can talk about science. And just with science, we have at least one inside project here at Argonne who's it's actually making transitioning to actually using quantum computers. So it's a Rosetta project. It's a protein folding. So problems like solving combinatorial optimization problems, this is where I actually have a lot of expertise in, and this is where actually it's one of the prime applications for quantum computers.
Oh, excellent point, Yuri. I appreciate all of those because in particular, getting access to these systems right now, like the 127 qubit IBM system, is not something that everybody in the country can do or provide. So definitely working with Yuri and other points of contact here are essential. And I do agree that optimization and this idea of mapping conventional problems over into the quantum mechanical space, very hot topic right now.
Yes, thank you.
Let's see.
So can I have a question? Yeah, Travis?
Yeah.
Hi. So I was curious because you just said that they passed the limit at which is possible to simulate the qubits on the regular or high performance supercomputers, right?
Right.
HPC system. So that's about what, 50 something, 60 qubits. So I was curious if now with the new system, it was possible to already show quantum supremacy.
Yeah, so this is the question about, well, you said quantum supremacy. I've started using quantum advantage, but it's the same principle. So in terms of can a quantum computer outperform a supercomputer, there has been very niche examples of this. There was an experiment back in 2019 in which the Google Sycamore processor basically did a self-check, right? It ran a random circuit just to confirm that it actually was running the random circuit correctly. And it turned out that the Summit system at the time could not keep up with that, that calculation. So the Google example of a quantum computer actually was solving this problem much more quickly than the best method available with the Summit computer was able to do. But there is a caveat to that, which is that there was nothing really computationally useful about that particular comparison. If I look at an example of a problem with, say, 127 or 80 qubits in the chemistry space, the chemistry problem that actually requires that few number of qubits is still relatively simple to solve, even on a conventional laptop. So we may need to push up the number of qubits within these systems to much bigger numbers before we're able to run application examples, computationally useful examples, that rival the best methods on conventional supercomputers. So I think right now the question of where is that threshold? Where do we cross the point where quantum computers are solving computationally useful problems that can't be solved with conventional approaches is still an unknown. But we have already passed the point where just simulating the device itself is now computationally infeasible.
Right. My question was addressing what you were clarifying, actually, in respect to practical problems. I remember even following the Google demonstration, there was another team in China that they proved to get even way faster, but again, it's just based on optics, but essentially is, again, not a very useful problem that they are solving. Yet they show that it can be accelerated hugely. The other thing that I was going to ask you, have you guys explored hybrid computing with the systems?
Yeah, great question. So in terms of hybrid computing, I often forget to mention it because it is such a natural concept to me. And I think this comes from my bias of thinking about accelerated systems. In every instance of these quantum computers being used, there is a conventional computer to which it is being hosted. And when I say that, I don't just mean that the control system is being hosted there. I mean that the domain logic, the programming workflow, how to actually interpret the results, this encoding, decoding step, all of that is part of the conventional computer's responsibility. There is a hope that we will move to a workflow in which a computationally hard task is handed off to the QPU, while some other task, which is better suited for a conventional system, is being processed, let's say, in parallel. And then eventually the results of those two tasks have to join each other. And that is the output of my program. There are some great examples of this being done in sort of a demonstration proof of concept setting. But again, what is the right task to hand off to the QPU so that you gain a computational advantage is a big area of discussion. You know, one of the other interesting things about that is how do you adopt quantum computing to conventional HPC workflows? There's been a number of efforts in languages and tools to try and perform this type of integration. I've seen extensions even to MPI, for which we might imagine communicating between quantum processors. I think all of that is kind of, well, it's the cutting edge of research right now in the field of quantum computing.
Maybe I can add this, given that this is HPC community, the easiest way to think about quantum device is essentially it's an accelerator, which is actually geared towards computing very, very specific tasks. Well, maybe like kind of like GPU, but GPU is more broad actually. QPU actually it's kind of like very good only at very specific targeted tasks. So pretty much by design, it's basically destined to be used as in a hybrid setup, and it's probably how to be done in future as well.
Yep.
If I may continue, I was just curious, does that mean that right now you're focusing on, or your team is just focusing on universal quantum computers? Because I've seen you're not using anymore the D-Wave machines, so no quantum annealing.
Yeah, so we actually are looking at 3 or 4 different models of computation. Universal gate models go back to the idea that if I have a set of instructions that are computationally complete, that I could design any program I wanted, at compile time effectively. The alternative is to use something with a restricted instruction set, so a special purpose device. And this is where quantum annealing fits in, is that as a optimization method, everything I do has to be cast as an optimization problem, or finding the lowest energy of a Hamiltonian, really. And there's many problems that can be cast into that framework. There is another model in which I actually try to compile down into the natural native dynamics of the device itself. So we call this analog simulation. Earlier I was saying we're controlling Schrodinger's equation, this partial differential equation. Well, what if instead of trying to discretize my representation into instructions, I just directly go and control the Hamiltonian itself in such a way that the results of that evolution represents the answer to my problem. And that's a natural model when we're talking about simulations of quantum mechanical systems. And then, of course, you can start to mix these models together. So I think all of these are on the table at the moment. And, in terms of which one is